right. So, I'm going to talk about catalysts in this lecture video, okay? Very briefly, we could spend weeks and weeks on catalysts, and I wish we could spend more time talking about it, but I at least wanted you to get a brief introduction on it, okay? And there's two types of catalysts that I'm going to talk about: homogeneous catalysts and heterogeneous catalysts, okay? So I'm just going to use a classic example of a homogeneous catalyst that you may have encountered in your classes. And that's the hydrogen peroxide decomposition catalyzed by iodine. Okay, so this reaction, okay, typically catalyzed by iodine. And so the first thing that I want to know about a catalyst, the classic definitions of a catalyst are that it reduces the activation energy. So you can see that in this graph right here, right? The uncatalyzed reaction has a much larger activation energy than the catalyzed reaction, okay? And so because of this reduction of activation energy, catalyzed reactions proceed faster. So let's see, lowers EA. The other classic definition of a catalyst is it is regenerated in the mechanism, which is what helps contribute to the speed of the reaction, not only in the reduction of the activation energy, but it keeps the reaction moving along, okay? So for example, this is the real mechanism for this reaction, and it's a lot more complicated than what you typically see in the classic textbook mechanism. So there's actually this rather complicated acid-base pre-equilibria. So this step is often referred to as the pre-equilibria step because it involves a hydronium ion donating a proton to hydrogen peroxide to make this rather odd H3O2 plus cation, okay? And so it's this cation that's unstable that can react with the iodine catalyst and make this HOI intermediate. So I'm going to circle the intermediate in red. And now this HOI intermediate will react with another hydrogen peroxide, regenerating H3O plus and the final product O2, but also regenerating I minus. So in fact, not only is this reaction catalyzed by iodine, but it can also be catalyzed by acid as well, okay? So we can see the intermediate appears as a product and disappears as a reactant. We've been talking about intermediates quite a bit. The catalyst, on the other hand, appears as a reactant and then gets regenerated as a product, okay? And so this is what we often think of this as catalytic cycles. So how many times can I minus be regenerated to keep driving this reaction round and round? I'm going to talk about that on the next slide with another example, okay? So that covers like the two classic definitions. A more descriptive definition that I really like to think of when I think of a catalyst is that it's a facilitator. So a catalyst, assuming I can spell, equals a facilitator, okay? So in other words, when we think about all the stuff we've been talking about in reaction dynamics, that the molecules have to collide, and not only do they have to collide, but they have to collide in the right spot, okay? Not all collisions are effective. Some collisions might result in a molecule bouncing right off and flying apart. Other collisions might involve a molecule finding that sweet spot right on the money and nailing it, okay? Catalysts are facilitators for that, or even we could think of them as a shepherd for the two reactants to find the sweet spot. This is less obvious in homogeneous catalysis And often in homogeneous catalysis, we see this rather complicated creation of unstable intermediates, okay? And by the way, what I didn't mention in this mechanism, right, because of that this step is very fast, okay, it is not rate contributing. It's not rate limiting. In fact, what becomes rate limiting on this step are these two steps right here, the pre-equilibria and the second step. So overall, the production of DO2 dt is dependent upon that catalyst, even though you might not see it at all in the final reaction. Okay? So in this homogeneous catalyst, the I minus creates this rather odd HOI intermediate, which then facilitates this last reaction that creates the stable product O2. Okay? So again, it's less obvious in a homogeneous phase, but I think when we get into the next couple examples that I'm going to describe, and particularly in heterogeneous catalysis, hopefully it makes sense, this definition of being a facilitator.